First question is, a circular disk of radius b has a hole of radius a at its center as shown in the figure. If the mass per unit area of the disk varies as sigma naught by r, then the radius of gyration of the disk about its axis passing through the center is. To get the moment of inertia of the disk, we have to take an elementary ring and then integrate to find the moment of inertia of the circular disk. So first we will take an elementary ring of radius r which has a thickness of say dr. This thickness is suppose dr. So elementary area of the ring will be equal to circumference, this is 2 pi r into thickness, so it is 2 pi r into dr. As density is given, this is the surface density or area density, it is sigma naught by r. Therefore elementary mass of the ring is sigma into dA, that is equal to sigma naught by r into 2 pi r dr. R and r get cancelled, so it is equal to 2 pi sigma naught into dr. This is our equation number 1. To find the total mass of the disk, we have to integrate this dm from r equal to a to b. This will give integral r equal to a to b 2 pi sigma naught into dr. This will be equal to 2 pi sigma naught into integral r equal to a to b dr, and it will be equal to 2 pi sigma naught. Integral will be r with limits r equal to a to b. First we will put upper limit, then minus, and then lower limit. So it will give 2 pi sigma naught b minus a. This is our equation number 2. This is the total mass of the disk. Now we have to find the moment of inertia. First, elementary moment of inertia for the ring, it will be equal to dm into r square, because we know the formula for the ring having the moment of inertia I if mass is m and radius of the ring is r. So it is I equal to mr square. Here ring has the radius is small r and mass is dm, so moment of inertia is di equal to dm into r square. So total moment of inertia will be, on integrating, we have integral dm into r square, and r is equal to from a to b. So it will be equal to integral. Substituting the value of dm, it is 2 pi sigma naught into dr into r square from limit r equal to a to b. So it will be equal to 2 pi sigma naught integral r square dr, where r equal to a to b. Integral of r square is r cube by 3. So we will have r cube by 3 with lower limit r equal to a and upper limit is b. Substituting the value, we have 2 pi sigma naught by 3, 3 is constant, and remaining is upper limit minus lower limit. Therefore, to find the radius of gyration, we know moment of inertia of the body will be equal to m into k square, where m is the mass of the body and k is the radius of gyration. This implies that k square will be equal to I by m. I we have calculated 2 pi sigma naught by 3 into b cube minus a cube. This whole divided by the mass of the body or the ring, a disk, and this mass we have calculated from equation number 2. It is 2 pi sigma naught into b minus a. This 2 pi sigma naught get cancelled, so it will be equal to b cube minus a cube by 3 into b minus a. On factorizing the b cube minus a cube, we will have b minus a into b square plus a square plus ba divided by 3 into b minus a. B minus a get cancelled. Therefore, k square will be equal to b square plus a square plus ab by 3, or k is equal to square root of b square plus a square plus ab by 3. Hence option C is the correct option. Second question is, a thin disk of mass m and radius r has mass per unit area sigma r equal to kr square, where r is the distance from its center. Its moment of inertia about an axis going through its center of mass and perpendicular to its plane is. Suppose given disk is have mass m and radius capital R, and mass density sigma r is given, it is equal to kr square. Therefore, mass increases as we move away from the center of the disk. To find the moment of inertia of the disk, we have to take an elementary ring and then find the elementary moment of inertia of this ring and then integrate to find the moment of inertia of the disk. So we take an elementary ring of radius say small r having the thickness dr. This is the elementary ring. So first we will find the mass of this disk in terms of the sigma. Elementary mass m will be equal to sigma r, this is the mass density, into area of the ring, which will be equal to 2 pi r into dr. So mass will be equal to integral r equal to 0 to r. That means we will take the first ring at the r equal to 0, that is at center, and then at the outer circumference. And this will be sigma r. Sigma r is given kr square and 2 pi r dr. 2 pi k is constant, so taken out of the integral, and remaining is r equal to 0 to capital R and then r cube dr. This r cube on integration will give r raised to the power 4 by 4 with limit r equal to 0 to capital R. On substituting, we will have upper limit, this is r raised to power 4 by 4 minus lower limit, it is 0. Therefore, the mass of the disk is 2 pi k into r raised to power 4 by 4. This is our equation number 1. Now in second case, we will find the moment of inertia. The moment of inertia of the ring, say di, it is equal to dm into r square, because for a ring, moment of inertia is mr square if mass of the ring is m and r is the radius of the ring. So this will be equal to dm is 2 pi r into dr into density, this is kr square, and multiplied by r square. So it will be equal to 2 pi k r raised to the power 5 dr. So integrating this elementary moment of inertia from r equal to 0 to capital R, we will have integral r equal to 0 to capital R 2 pi k r raised to power 5 dr. 2 pi k is constant, so taken out of the integral, and remaining will be r raised to power 5 dr. This r raised to power 5 on integration will give r raised to power 6 by 6 and limits from 0 to capital R. So this will give 2 pi k capital R raised to power 6 by 6 by substituting upper limit, and then lower limit, it is 0. So finally we will have 2 pi k into r raised to power 6 by 6. This is our equation number 2. Now to find the moment of inertia, we will divide the equation number 2 by 1. We will have 2 divided by 1. It will give I by m, that is equal to 2 pi k r raised to power 6 by 6 divided by 2 pi k r raised to power 4 by 4. This 2 pi k get cancelled, so it will result in r raised to power 6 by 6 into 4 by r raised to power 4, that is equal to 2 by 3 r square. So moment of inertia in terms of mass m will be equal to 2 by 3 m into r square. Hence option D is the correct option. Third question is, the moment of inertia of uniform semicircular disk of mass m and radius r about a line perpendicular to the plane of the disk through the center is. It is given that semicircular disk have the mass capital M and radius small r. We know that moment of inertia of a disk about an axis perpendicular to the plane of the disk and through the center is half mr square if m is the mass of the disk and r is the radius of the disk. So if we consider this is the whole disk, then other part will also have the mass m and radius r. So effectively this is a disk which has the mass equal to 2m and radius equal to r. Therefore, we can say that moment of inertia of the given disk will be equal to half into mass of the disk, this is 2m, and radius is r square, and it will be equal to m into r square. Hence, moment of inertia of the semicircular disk which will be half of the total disk, and it will be equal to 1 by 2 of disk, and that is equal to 1 by 2 m into r square. Hence, option D is the correct option. Fourth question is, one quarter section is cut from a uniform circular disk of radius r. This section has a mass m. It is made to rotate about a line perpendicular to its plane and passing through the center of the original disk. Its moment of inertia about the axis of rotation is. Suppose the disk is having the radius r, and from this disk one of the quarter is cut. So this quarter is the 1/4 of the original disk, and this quarter has the mass capital M. So we can say that total mass of disk will be equal to 4 times of the M, and radius of the disk is R. So moment of inertia of the disk about the center O through which the axis of rotation is passing perpendicular to the plane of the disk is 1 by 2 mass of the disk, which is given 4m into r square. So it is equal to 2m r square. And because quarter has the 1/4 of the total disk, so moment of inertia of the quarter of disk about the axis through center of the disk will be 1/4 of the IO, and it will be equal to 1 by 4 into 2 mr square. Hence it is equal to 1 by 2 mr square. Option A is the correct option. Fifth question is, from a uniform circular disk of radius r and mass 9m, a small disk of radius r by 3 is removed as shown in the figure. The moment of inertia of the remaining disk about an axis perpendicular to the plane of the disk and passing through the center of the disk is. We will use the formula that moment of inertia of the remaining portion will be equal to moment of inertia of the total body minus moment of inertia of the removed body or the cavity about the same axis of rotation. So first we will use I total. This will be equal to, because for a disk having the mass m and radius r, the moment of inertia about the axis through the center and perpendicular to the plane will have the formula I equal to half mr square. So we will have half into mass is given 9m and radius is r. So we will have total moment of inertia is 9 by 2 mr square. This is equation number 1. Second, remove portion is also disk, and it is having the radius r by 3. We know that mass is 9m and it is equal to density into area. This area is pi into r square. Now we have removed the portion which has the radius r by 3. So mass is say m dash and density is same, and area is pi into r by 3 square. So from these two equations we can write that m dash by 9m will equal to rho pi into r by 3 square divided by rho pi r square. So this gives m dash is equal to 9m into 1 by 9, that is equal to m. So we can say that moment of inertia of the cavity about the axis passing through the center of the original disk will be equal to 1 by 2 m into r by 3 whole square. This is the moment of inertia of the disk about the center, say it is O dash. Originally it is O. So this is the IO dash. Now we will use the parallel axis theorem. The distance between these two parallel axes is 2r by 3, and mass of the disk we have calculated m. So it will be m into 2r by 3 whole square. This formula is written using the parallel axis theorem. So we will have mr square by 18 plus 4 mr square by 9. So this will give 18 mr square into, and then it is 9. So it is equal to mr square by 2. This is our equation number 2. Therefore, Moment of inertia of the remaining portion about the axis passing through the center of the original disk and perpendicular to the plane will be equal to I total minus I cavity or remove portion, and it is equal to, from equation 1, I total is 9 by 2 mr square, and from equation 2, I cavity is mr square by 2. So it is equal to 1 by 2 mr square into 9 minus 1, and it is equal to 8 by 2 mr square, and it is 4 mr square. So option B is the correct option. Sixth question is, seven identical circular planar discs, each of mass m and radius r, are welded symmetrically as shown in the figure. The moment of inertia of the arrangement about the axis normal to the plane and passing through the point PH. In the question, the inner disk is suppose disk 1 and other are 2, 3, 4, 5, 6, 7. The arrangement is symmetrical. Therefore, if we find the moment of inertia of the first disk about the O, this will be equal to 1 by 2 mr square as per the formula for the circular disk about axis passing through center and perpendicular to plane. Similarly, if we find the moment of inertia of the disk 2 about the O, so we will use parallel axis theorem. First, the moment of inertia of this disk about its own axis through the center perpendicular to its plane will be half mr square, and then through the parallel axis theorem, the mass is m and distance between the centers of the disk 1 and disk 2 will be 2r, so it is 2r square. Hence, we can write that is half mr square plus 4 mr square, that is equal to 9 by 2 mr square. Because arrangement is symmetrical and there are 6 disks around the disk 1, therefore the moment of inertia of I20 plus I30 plus dash dash and I60 will be equal to 6 times of the 9 by 2 mr square, that is equal to 27 mr square. So we can see that total moment of inertia about the O will be equal to I10 plus I20 plus and so on to I70, and that will be equal to half mr square plus 27 mr square, and this will be equal to 55 by 2 mr square. This is our equation number 2. Now we have to find the moment of inertia through the axis passing through P and perpendicular to the plane. We have to use parallel axis theorem, so IP will be equal to IO plus total mass. Now total mass at O will be 7m. This is the total mass. And distance between the O and P is, this is R, R and R, that means 3R. So we will have 3R square. And substituting the value, I0 is 55 by 2 mr square plus 7m into 9r square. This is equal to 55 by 2 mr square plus 63 mr square, that is equal to 181 by 2 mr square. Hence option A is the correct option. Seventh question is, a circular disk D1 of mass m and radius r has two identical disks D2 and D3 of the same mass m and radius r attached rigidly at its opposite ends as shown in the figure. The moment of inertia of the system about axis OO dash passing through the center of the D1 as shown in the figure will be. For the disk, we know that moment of inertia I is equal to 1 by 2 mr square for the disk having the mass m, radius r through the axis of rotation passing through the center of disk and perpendicular to its plane. In the disk 1, the axis rotation is through O and is perpendicular to the plane of the disk. The moment of inertia will be half mr square. This is our equation number 1. Now we consider the disk D2 and D3. Because both are identical, so we will consider one and then same will be applicable for other disk. For disk D2, if we consider the center, then axis rotation will be through say O2, and we then take the perpendicular axis to find the moment of inertia about the diameter. After calculating the moment of inertia about diameter, we will use parallel axis theorem to calculate the moment of inertia of the disk D2 about the axis OO dash. So first, moment of inertia of disk D2 about the axis through its own center O2 will be equal to half mr square. Then, using the perpendicular axis theorem, the moment of inertia of disk D2 about its diameter will be half of the moment of inertia about its axis through center. It will be half mr square, that is equal to 1 by 4 mr square. And then using the parallel axis theorem, moment of inertia of D2 about OO dash will be equal to 1 by 4 mr square. This is the moment of inertia of the disk about its own diameter plus mass of the disk is m and distance between their centers. So these parallel axis has a distance of r. So it is mr square. Therefore, we will have it is 5 by 4 mr square. This is equation number 2. Similar value will be for disk D3 for about the axis OO dash will be also equal to 5 by 4 mr square. This is equation number 3. So total moment of inertia will be equal to I d1 about O plus I d2 about OO dash plus I d3 about OO dash, and it will be equal to half mr square plus 5 by 4 mr square plus 5 by 4 mr square, and that is equal to 1 by 2 mr square plus 5 by 2 mr square, and it is equal to 6 by 2 mr square, or we can write it is 3 mr square. Hence option C is the correct option. Eighth question is, a circular disk of radius r and thickness r by 6 has moment of inertia I about an axis passing through its center perpendicular to its plane. It is melted and reshaped into a solid sphere. The moment of inertia of the sphere about its diameter is. We are given a disk which has the mass, suppose m, radius is having r, and thickness is r by 6. It is reshaped in a solid sphere. Its mass will be same m. We have to find its radius, say r dash. Therefore, moment of inertia of the disk will be equal to 1 by 2 m into r square. This is the moment of inertia of the disk. Now, moment of inertia of the sphere will be equal to 2 by 5 m into r dash square. So we have to relate this r dash. Because mass is same, so we can write that mass equal to density into volume. Therefore, for disk, it is density is same, so it is rho into area will be pi into r square, and thickness is r by 6. So this is the mass of the disk. On reshaping, mass remains same, so it will be equal to density into volume of the sphere. It is 4 by 3 pi r dash cube. Therefore, this rho and rho get cancelled, pi and pi get cancelled. We will have r cube by 6 is equal to 4 by 3 into r dash cube. This implies that r dash cube will be equal to 3 by 4 into r cube by 6. It get cancelled by 2, and we will have r cube by 8. This implies that r dash is equal to r by 2. Now we will use this value here. So the moment of inertia of the sphere will be equal to 2 by 5 into m into, and then r by 2 whole square. So it will be equal to 2 by 5 into m into r square by 4, or it is equal to m r square by 10. So moment of inertia of the sphere divided by moment of inertia of disk will be equal to mr square by 10 divided by, it is half mr square, and that will be equal to 1 by 5. So we can say that I sphere is equal to 1 by 5 of I disk. And because moment of inertia of the disk is given I, so it is equal to I by 5. Hence option C is the correct option.